So welcome everybody. Today's topic is going to be around theory of everything, and we will see where that goes and what that means. But maybe just a brief introduction, like our starting point can be as elementary as classical mechanics and some of the laws of physics that most of us have learned in school. So maybe we start with classical mechanics and the idea of Isaac Newton, and we have the theory of motion. So maybe, Katy, you can begin with what we start from school when it's classical mechanics.
Yeah, sure. So in the classical picture that we have, so Newton was really concerned with gravity. Everyone knows the story about the apple falling from the tree. And what was kind of beautiful about Newton's theory of gravity is that it unified the idea of sort of small-scale physics, what happens when an apple falls to the ground, and things in our solar system or even in galaxies and in our universe, where you have large-scale gravitational phenomena like orbiting planets. But his whole picture is classical. So his whole picture is the kind of physics that we normally, we have an intuition for, where things follow a well-defined path. So if I throw a ball and I throw it in the same way, it always takes the same trajectory through space. It always lands in the same place. And that is, how we think the world works until we get on to perhaps quantum mechanics.
Yeah. So, Toby, based on this, what Newton... So, these were based on the earlier observations which were already on board by Galileo and other things, right? So, he was basically trying to formulate a structure of how should we go about doing this business, so if you can.
What Newton did, I think, was unbelievably remarkable in the sense that he gave us not only the theory of gravity, as Katy said, but he also developed calculus in order to understand how to write down the theory in the first place. Yeah. And so really he gave the idea that you could describe phenomena of the real world using mathematics. And before that point, it just wasn't clear how to do that. So it was a complete shift, in a paradigm shift in how we think about describing the world. And in many regards, even today, his Newton's laws still work. Provided you're looking at large scales, Newton's laws are the way, and certainly intuitively, the way we understand the world. It's an incredibly successful mathematical framework, as Katy says, and this is no criticism of Newton, but when you look on very small scales or very high energies, in fact, in detail, Newton is wrong, and his theory gets replaced, his theory of Newton's laws gets replaced by quantum mechanics, but for everyday phenomena, that's not necessary, and his laws are quite remarkable.
So then, after Newton proposes these laws of motion, so when people started to look at different kinds of things, for example, light, and then we move on to even smaller things and that has the different sets of laws of motion, how did the structures change?
So there was a very interesting period in the early 1900s, sort of around 1910 to 1920, when a range of experiments were indicating that there were problems with the classical world of Newton. And a lot of this was around atomic physics and light and how materials interact with light. Things called photoelectric effect, for example, was one of the key points at that time. And a collection of very brilliant people, Schrödinger, Heisenberg, Bohr, Born, and so on, those names we associate with quantum mechanics now, sort of all came together and developed this completely new theory of how the world works, in the sense of, and by works, what Newton did was say, if I know the state of the world now, I can predict it in the future. And Newton said, in fact, if I really knew precisely the state of the world now, I can precisely tell you what it'll do in the future with no uncertainty. It was then understood was that there is a way of trying to understand how to map the state of the world now if you could measure it to the future. It's not Newton's laws, it's quantum mechanics. That theory was written down in a very short space of time, sort of less than 10 years, but it has a very different nature than Newton's laws, a very different nature, to the point where lots of people don't like it. Einstein didn't particularly like it. Still people today don't like it. But it's a very, very structurally different theory. So even though it's compatible with Newton's laws in the sense that when you go to a regime of large energies or large scales, so the quantum effects become unimportant, you do recover Newton's laws. But if you're in these more exotic quantum regimes, like if you're looking at individual atoms or you're looking at very high energy phenomena, it structurally is very different. And it's very different in two ways. One is the way it describes the state of a system. It's got a massively, massively bigger possibility of states than normal classical mechanics, which is that's the basis of how quantum computation will work or does work. That's where it gets its advantage from. But the other important point is it's not deterministic. So you can only know so much about the state of a system at a time. There's fundamental limits to how well you can know it. And even if you did know it and you sort of wound the clock forward, you could only probabilistically say what will happen later. Apparently you can't know what will happen later. So it's a radically different theory.
Yeah. So Katy, you have been working on gravity. So under this structure of quantum mechanics and classical mechanics, how does gravity come in, and then how does this play a role in reconciling or not reconciling the two structures?
Right. Well, so this is really the problem. Is, what we would like to do is to combine these two theories. And in general, when we're talking about gravity, we're talking about very large scale phenomena. We're talking about planets, galaxies, even black holes are relatively large things, and therefore they obey the classical laws as far as we can tell. Whereas when we're talking about quantum things, we're talking more about small scales, very high energies, very short length scales. And in both of these cases, we can kind of do without the other. So when we're talking about gravity on large scales, we don't usually need to think about quantum mechanics. And when we're describing quantum mechanics, we don't really need to think about gravity, because locally things, aren't really affected by gravity. So we have this kind of complete separation of scales. But we nevertheless believe that at some level we should be able to reconcile these descriptions. And particularly in the case of black holes, if you take a black hole and you really take it to its sort of logical conclusion, which is that, a star collapses and it really becomes a sort of a point at the center of the black hole, we lose our ability to predict what happens there. So at that point, we call it a singularity, but really what we mean is we don't know what happens there. So singularity is the kind of the word that physicists use to say all the equations break down. We can't predict what happens there. And no one really believes, I think, Toby can disagree with me, no one really believes that a singularity really exists, it's really a thing, right? People think that somehow either quantum mechanics will come in and change things, some higher energy phenomena will come in and regularize that infinity that happens in the center of a black hole, or, gravity will somehow change its nature and stop being classical, and maybe space and time will become in some way fuzzy in a quantum mechanical way that will, again, we'll be able to predict things that happen at the center of a black hole, but maybe in a probabilistic way instead.
So other than the scales that where classical mechanics laws are applicable and quantum mechanics laws are applicable, philosophically or structurally, what is the stopping point that you cannot really put these two together? It's like, what's the key radical difference?
So yeah, we were chatting about this a bit before, and we were a little bit arguing about what we thought was really the obstruction. So I would say, so in my mind, the way I always think of it is that you can start to describe gravity in the same way as you describe particle physics. So you might have heard of gravitons. So graviton is the kind of particle description of gravity, and we can write down a theory of gravity where you have gravitons and they would kind of scatter off each other. But when you take that theory to the sort of high energy limit, it breaks down. You get infinities that you can't remove. So for me, this is always the kind of manifestation of the fact that we can't get this complete theory, because somehow when we apply the techniques of quantum mechanics that we would normally apply for things like electromagnetism to gravity, we can't sort of follow it through. Our calculations sort of break down and stop working.
I don't think we disagree.
Okay, we don't. That's a relief.
I think one of the important points to take away, often people hear we can't reconcile gravity and quantum mechanics. We don't have a theory of quantum gravity. Those are often the words you hear. And I don't think that's true, or you have to be careful what you mean. So Katy was describing in gravity, space and time in Einstein's theory of gravity become dynamical and can ripple, just like the surface of a pond ripples, and they're what we call gravitational waves. And since 2015, we've actually observed these things remarkably. But when you make gravity quantum mechanical, it's possible, we think, to make those ripples quantum mechanical. So we know how to do that. So it's not hopeless in making general relativity quantum mechanical. But as Katy says, the question is, when mathematically, how complete is that? So does it work for all ripples, or does it only work for sort of quite long wavelength ripples? And so our understanding of it is that it works for long wavelength ripples. So if you walk around and create some ripples in space-time, we could probably make them quantum mechanical. But if you think about the sort of ripples that are falling into a black hole near the singularity, or you collide very, very high energy ripples together so that they form a black hole, we can't, that mathematically doesn't work anymore. So there is a limit. It doesn't describe, we can't have a complete quantum theory of gravity. But it's not that gravity and quantum mechanics are completely incompatible either. We think they're compatible. We just can't understand them completely.
Right. So this being the problem, I think Einstein in his last few years, he started to have this idea if this can be put together and maybe we can have a theory of everything. So was it a mathematical challenge? Was it a philosophical challenge, or was it both?
Well, so I think the story of theoretical physics over the last 100 years or so has been, it's had remarkable success in describing phenomena with increasingly simple theories, and that culminated with what we call the standard model of particle physics, which sort of got finalized in the 70s. And you can literally write it on a t-shirt. So actually I had a hoodie with it written on, but I thought it was a bit warm to wear, so I didn't, but I probably should have done. But it really is, it's a couple of lines of equation that if you're a fourth year physics student and you've done the right courses, you can understand what it means. And it pretty much mathematically describes every phenomena, excluding gravity, that we've ever seen or described or measured. I mean, it's remarkable. That's the Higgs particle, all of material science, all of biology, maybe not consciousness, we don't know about that, but, barring whatever goes on there, it describes everything, and it's, exquisitely tested. And so this simplification, I think, has led to the idea that actually maybe we can write down an equation that describes everything. And Einstein started doing this quite early on, based on even earlier work in the 1920s in a very sort of beautiful formulation called Kaluza-Klein theory, which I won't go into, but it's essentially a theory of space and time which pops out both Einstein's gravity and electromagnetism. And so Einstein in the 50s, towards the end of his life, was already trying to sort of unify other bits of particle physics into one framework of space and time, sort of actually way ahead of his time. There's this perception that he was just doing nonsense when he was old, and it's not true at all. I mean, there's two fallacies about him. One is he didn't understand quantum mechanics, which is nonsense. He discovered many of the really important ideas in quantum mechanics. He didn't like what it was saying, but it didn't mean that he didn't understand it or do brilliant research on it. And also this idea of unification. He was a very early adopter in that.
So, Katy, you have been working on theories of gravity. So, when Toby says that one of the things to think about, or the direction to go about, is to think of one single equation that can describe everything that we know, right? So, in this context, going forward from Einstein, how does extra dimensions come in, and then how does the next stage go?
Right. So, yeah, I mean, there are kind of two approaches to trying to figure things out. There's the kind of top-down approach, and there's the bottom-up approach. So, the top-down approach is something like string theory, where you say, you really start with a whole different description of what particles are. Maybe they're not particles, they're actually excitations in some string, right? So you're really starting from almost a sort of a new concept, and then you're trying to get down from that to what we observe, which is gravity and particles and things like that. And then the other way is to kind of, modify gravity. So to try and add extra terms into Einstein's gravity. And then if you can measure those terms in nature, that might give you a clue of how to go kind of upwards. And, people work from both directions, trying to go sort of up and down. On the sort of top-down approach, we've done some simulations in higher dimensions to try and understand how having higher dimensions affects gravity. We've also done the bottom-up approach, where we try and add in these additional terms and then see if we can observe them in the gravitational waves that we're seeing from detectors now. So I think both approaches are valuable. And, in a way, we're just looking for like a hint, right? We're just looking for a kind of a pointer in the right direction. That's how it feels at the moment. And whether that comes, as I say, from a kind of bottom-up approach or a top-down approach is something that we'll just kind of have to wait and see, I guess. I don't know, Toby. I think you work more from the top-down approach. So what do you think?
I think we're in a funny situation in terms of trying to make progress. We're in a funny situation where we don't... I'm going to blame the mathematicians. Okay. So they're quite impressed with themselves, but the bottom line is it's very limited what we can solve mathematically. So many of the theories we've written down in physics are just too advanced for the mathematicians to deal with, and they can't solve them. This is true even for our model of what we call the standard model of particle physics. So, for example, the theory of the nuclei of atoms. So the fundamental theory of it's something called quantum chromodynamics. Again, it's a thing, part of the thing that you write on your T-shirt, but mathematicians haven't got to grips with how to solve those equations. In fact, if there's any kids in the audience and you learn some calculus at school, you'll learn to integrate things. Some of you will remember back. And it's just a scam, because you only ever get told things that you can integrate, and no one tells you almost nothing can be integrated. And so you left school with this illusion that this beautiful mathematics works. You just weren't clever enough to figure it out. But it's nonsense. So it's very limited what we can do. And, there are some areas like string theory where the maths is a little bit more advanced than in other areas, but it's very tough to make progress mathematically, even to understand whether the theory that we've written down is really consistent just at the level of mathematics, whether the equations really are self-consistent with each other. On the other hand, observationally, because the standard model of particle physics and gravity, Einstein's gravity, do such a good job, there isn't a clear hint. There are some clear hints of mysteries in the universe that we don't really understand, but they're opaque at the moment, and it's not really clear how to think about them or what to change or what to do next. So, there are various different approaches we've heard about. But I don't know what the answer is.
I can't believe you blame the mathematicians.
I'm
awful.
Always blaming the mathematicians.
I'm in a maths department. I disagree with Toby, for the record. Mathematicians are great.
Toby, since you mentioned QCD, the quantum chromodynamics, this was the breeding ground for string theory, right? And string theory is one of the foremost candidates to take over the theory of everything. What is the key idea in string theory that reconciles this fundamental aspect that quantum mechanics, a probabilistic theory, we really cannot determine everything? On the other hand, a classical mechanics is everything is deterministic.
Okay. So one important thing to say about string theory is it sounds tremendously exotic, but actually it doesn't change anything about quantum mechanics. It's completely standard from the point of view of quantum mechanics. Other approaches to quantum gravity often modify quantum mechanics in very funny ways. So in some ways, string theory is actually rather conventional. It was originally written down as a theory of the atomic nucleus, essentially as a theory of the interactions between neutrons and protons, or what are called the strong interactions. And it failed at doing that. And then the theory called QCD came along, which explained everything brilliantly. And so string theory was then dropped. But it was then realized a little bit later in the 80s that actually a modified version of string theory, which wouldn't be good for describing atoms and nuclei, in fact included in it a full theory of gravity. And it's a fully quantum theory with a few caveats. It's basically a good quantum theory that seems to exist at all energies, and so it makes sense quantum mechanically, mathematically. And yet, within it, a part of it is a theory of gravity. And so that was a huge surprise, because no one was trying to, no one wrote it down thinking, I want to explain gravity. That's not how it arose. So it arose very much by chance. And then even later in the 90s, it was then understood that several different string theories that have been written down, which all looked a little bit different, but they were in fact all related to each other by what we call dualities, so by some symmetries. So in fact, they weren't really different theories. They were all just the same theory looked at in slightly different ways. And so in the 90s, there was a lot of excitement about it, because this is a theory that seems to be mathematically consistent with quantum mechanics, fully mathematically consistent. It includes gravity, and it looks like there's just one theory. And so you start thinking, well, okay, hang on, maybe this is it. Now, more recently, then there was a lot of work on it, trying to, in detail extract our world. Now, one of the first things you come across is the fact that it wants to live in 10 dimensions or 11 dimensions, as you may have heard, which sounds obviously terrible, but it's entirely plausible in this theory that 6 or 7 of the dimensions are wrapped up into a sort of very small geometry that we can't see. That's perfectly reasonable, but unfortunately, there's partly as a result of that, there's actually many different theories at low energies where you can't resolve these very small 6 dimensions or 7 dimensions. There's unfortunately very many things that it can produce at low energy. So it can produce things that are apparently compatible with our world, but it can produce all sorts of other things. And so there's no sort of smoking gun where you can say, aha, our world must be string theory, because actually it could produce a gazillion different worlds. And so the perspective then changed a little. And to this day, there isn't really, it's still believed to be a mathematically consistent theory. It's very beautiful mathematically, but we can't say for sure, knowing with the observations we have, that yes, string theory is right. It's not, lots of people have sort of heard in the media that it's untestable, and that's just not true. It's untestable currently, we think, but if you could build a collider that was big enough and scatter things together, you would see strings. It's completely testable. It's just not using current technology. So it's not testable in the sense that the Greeks' theory of atoms wasn't testable at the time. They were right, but it wasn't reasonable that they could test that they were correct.
Right. Yeah. So, Katy, you have worked quite a lot on cosmological scenarios.
Yeah, so there's a kind of a hope that cosmology will give us the answer. So, at some point, our universe, if you rewind it backwards in time, the scales get very small. So, even if now we don't have access to the kind of high energy scales where we would see strings, for example, maybe somewhere in the early universe, we hit that scale. And at that time, there was some emission of gravitational waves, is something, that's a popular idea, that we could observe now that would then give us some kind of clue as to what happened in the early universe. So it's really about accessing these kind of scales. And in a sense, I always think, cosmology is the better bet compared to black holes, because black holes, you have this horizon beyond which you can't see anything because light can't escape from the horizon. So you could, in principle, jump into a black hole, and then you could, if you survived, which you wouldn't, but if you did, you could fly to the center of the black hole and then say, oh, strings, that's great. You're right. But then you can't get back out again. So, okay, maybe you have the satisfaction of knowing for a brief moment that you were right if, you're a string theorist. So maybe we should throw more string theorists into black holes. Sorry, Toby.
Throw the mathematicians.
Yeah, okay. All right, we'll put the mathematicians in. So, you could know, but, we can't ever access that from the outside and then, go and do other experiments. So that's really unsatisfying. And actually, the problem is that, well, as far as we know, black holes have a kind of a size. And what we would really like if we wanted to probe kind of quantum gravity scales is we would want really tiny black holes. And we don't know how to generate really tiny black holes. So there are some theories which predict them being produced in the early universe. So as I say, these kind of cosmological scales where we go backwards in time and we go to the early universe where we have small scales might be our only opportunity to really probe with observations these kind of scales. So I work on both. Actually, at the moment, I work more on black holes, so I probably shouldn't say black holes aren't a good way to study this. But sometimes I think maybe cosmology is going to be the only clues we get.
Can you elucidate a little bit more about cosmic microwave background? Gravitation waves can help to talk about the extra dimension.
Well, I mean, so something like string theory, for example, predicts extra dimensions, and one of the challenges is for string theory is that obviously we don't see them. So if they played any interesting role, they have to somehow arrange themselves to be hidden away today. Now, I'm not sure I can say very much more than extra dimensions. If they're there, they're not evidently very visible to us. I mean, what I would say is I would definitely agree with Katy. One of the other hints I think we have that there's something wrong with the way we're thinking about the universe is this thing called dark energy or cosmic acceleration. So it was discovered. I mean, during my PhD, in fact, was when they discovered it, and it was a huge surprise to everyone because people had considered cosmic acceleration way back. Even in the sort of 20s, people had understood that it was possible in Einstein's equations to write down this term that led to an acceleration expansion. But even in the 20s, there was a famous British astronomer called Arthur Eddington, who is quite well known, who understood that if this term was there, it had to be incredibly small, because otherwise it would just ruin observations. You can't have the universe just accelerating in front of you. For a long time, people assumed that acceleration had to not be there. And so it was a big surprise then in sort of late 90s when it was actually shown that it's there, but it's, in terms sort of mathematically speaking, incredibly small. So it's an incredibly small amount of acceleration, and small to the point where it's only in the last few billion years of the universe that it's become important, because before that the universe was more dense, all the other matter was far more important than this very weak acceleration that's acting. And so it's only come to dominate now. And so there are two aspects of it that are sort of very concerning theoretically. One, it's not zero, but it's very, very small. So how does that work mathematically? And secondly, why does it come to dominate today when we're looking rather than 500 billion years in the future or way back in our past? And this is called the cosmic coincidence problem. And both of these are very fishy. So, we're at a state in cosmology where, if you ask many cosmologists, they'll say, oh, we've got a wonderful theory of cosmology. But they're not really being honest, because if you really try and understand it at the fundamental theory of everything level, with quantum mechanics included, it looks very peculiar. And so to me, it may be a hint. That may be cosmology's biggest hint, that there's just something we're getting wrong. Maybe it's to do with the way we're observing the universe, we're measuring the universe. And so naively, when we think quantum mechanics is very important on, atomic scales, small scales, maybe when we're in a universe and we're measuring it, maybe the rules of quantum mechanics are, we don't really know how to apply them to ourselves in the universe, the observers within the universe. We really understand them in the lab setting when you're looking at an experiment and you don't think about yourself as being part of that experiment. So maybe there's something, that's my hope.
So, Katy, would you call this some kind of a fine-tuning problem, or would you rather say that it's more generic, like we don't understand the fundamental theory?
Yeah, I think I always believe that we just don't understand the full theory. It's even a kind of philosophical question of where do we stop? Like, what's the truth? So it's not our business as scientists to try and determine what the truth is. Really, we're just in the business of building models that describe the observations we see, and we can use them to predict new phenomena. And if they're consistent, we say that's a good model. But it's always a model, right? Like it's maybe just an analogy that we use to describe what we see. But the truth, that may be something that, maybe we can't even get our brains around as humans. So I think, when we see something that we don't understand, that doesn't fit our model, or that doesn't fit the analogy that we use to describe it, that's a lack of understanding on our part. There must be some fundamental reason. Maybe we can't understand that reason. Maybe it's not possible. Maybe we don't have the capacity to understand it. But yeah, at some level, there must be an explanation for these things.
Now, let's moving on from string theory. Are there any other candidates which can challenge this? And then if there are, then to what level and to what extent should we have this?
Well, yeah, so there's lots of candidates. So there's, string theory is one. Loop quantum gravity is another. Spin foams, causal sets, in Java gravity. There's many, many different approaches to thinking about how to write down a quantum theory of gravity. Most of the non-string theory ones start, as Katy was saying earlier, they start with Einstein's theory and then try and make it quantum mechanical in a different way than the obvious way, because the obvious way runs into these problems that it doesn't give you a complete theory. It works to some extent, but not completely. So in some sense, they're more radical, even though they start with Einstein's gravity, which seems like a good starting point. They're a bit more radical because they usually modify our notions of quantum mechanics in some way. Loop quantum gravity, for example, certainly applies quantum mechanics in a different way than you would normally apply it to, say, atoms. Now, all of these theories have their virtues and their failings. String theory's virtue is that we mathematically can control it much better. So we're pretty sure it gives a theory of quantum gravity. What we're not at all sure about is whether it's our world or not. Something like loop quantum gravity, the mathematics, as I was saying, again, I blame the mathematicians, the mathematics, just isn't well developed to deal with it. And so we can't even be sure that it really gives a theory that reproduces the classical physics of Einstein's gravity, which is, if it can't do that, it's not a theory of gravity at all. So the status of most of the other theories, in fact, I would say nearly all of the other theories, is actually even weaker than string theory in the sense that maybe they start from thinking about a four-dimensional theory of gravity. They try and apply some quantum mechanics to it. But at the end of the day, it's very unclear that it spits out classical gravity, classical Einstein gravity in 4 dimensions. By 4 dimensions, I mean 3 space, 1 time, where it should. So none of these opposing theories really are convincing mathematically, I would say, at the moment. But, I'm very much of the opinion, you may have read in the news, there's lots of sort of my theory is better than your theory going on, or, string theory is not even testable. We've talked about that. I think it's all a bit naive, to be completely honest. I mean, I don't know what the answer is, but I'd be very surprised if anyone's written it down. Particularly when you think about what we're trying to understand. I mean, we're literally trying to understand the laws that govern everything. I mean, we've come a long way in not very long. And we have we do have the laws of particle physics, which govern all of matter, maybe not gravity, but all of matter to an incredible extent. But I think that was, in good measure, good fortune. And should we expect to have written down the theory of everything, within a few decades after? I mean, I don't know it would be remarkable if we had done. So I don't think any of them are right, probably. There's lots of competitor theories, but it's very murky still.
And from the testability point of view, like from cosmologically or from particle physics,
the problems are not even getting to the level of asking, does it reproduce cosmology, I think is missing the point, in the sense that we don't know whether most of these theories even reproduce a notion of space and time. So forget cosmology. I mean, does it reproduce, 3 space, 1 time dimension and basic gravitation between 2 masses? Without that, there's no point, I would say, even wondering whether it describes cosmology and so on. Right. But I am a pessimist.
I was going to say, I think Toby, we were supposed to end on a positive note. But
so
tell me when we're ending, and I'll be positive.
So it seems that there is a long way to go, even for string theory, to come to the universe that we observe today, at least to some extent. I mean, one can still think about other ways of dealing with this problem. One thing that we were discussing before was to have this emergent phenomena where maybe not classical mechanics or quantum mechanics are fundamental, maybe space-time itself is not fundamental. Something else are there, and that's whatever we are observing are emergent.
Yeah, my view is that everything is emergent. That really, space and time and, all the things that we describe with our models are in some ways just our interpretation or our approximations of some more fundamental reality that, maybe we can probe or we can't probe. So I would say that everything is, in some sense, emergent in that way. But that doesn't necessarily, unfortunately, give us a kind of clue as to what that deeper reality is. So I think the real hope is to have some kind of hint from observations. So Toby talked about dark energy. I think that is a big hint that we've got something wrong. And if we can figure that out, it might be the key that we need to go a bit further. I guess in general, I am a bit not so hopeful about the top-down approach. It seems like maybe that's too complicated for us to do it that way around. It would be great if we could. But in general, we get, science is driven by observation. So my hope is that we see new things in our experiments that give us a kind of hint of where to go next. And, we do have a lot of exciting observations. So I'm trying to be the positive one now, Toby, to counteract you. We do have a lot of exciting observations coming up. So we talked about gravitational waves already. I don't think it can be overstated how exciting these new observations of gravitational waves are. It's like, with gravitational waves, they're a new messenger from the universe. And it's like when we were looking through a telescope with just visible light at the stars. We're at that phase with gravitational waves. And when you think of where we went from Galileo looking through his telescope to the kind of, telescopes we have now that look at all kind of phenomena in the infrared or in radio waves, every time we open up a new band, we see new things. And we have that future ahead of us with gravitational waves. We're going to look at gravitational waves on all scales, coming from almost the whole observable universe in future telescopes, right back to the very beginning of the universe. So there is a huge discovery potential there. And so that's my hope, is that the hints will come from these observations.
And I could also, to be optimistic, the mathematicians might make some progress.
But you're not holding your breath, Toby.
Before we end, I would like to ask, for the next 5 years, let's say the world survives and we are, the mathematicians survive. So next 5 years, if you are given the next 5 years to work on the theory of everything, starting from whatever we have discussed or whatever we have to today, the startup, let's call it theory of everything startup. How would you plan the next 5 years?
You go first, Katy.
Thanks, Toby.
You sound like a grant funding
council. I was going to say, what was your last grant? So I would say, for me, gravitational waves, well, partly because that's what I do. That's what I'm good at. In a way, you have to kind of pick your path and then hope that that's the good path. You never know. So my research is mainly modeling these kind of gravitational waves that we get from different phenomena in the universe. We can't model everything, but we would like to be able to understand if there were some deviations there from our standard theories of particle physics and from cosmology and from black hole physics, general relativity, what would they look like? And as Toby already said, the mathematics is often the barrier. Often these systems are so complicated that we can't just write down a solution by hand as to what they would look like. So we do computational simulations of what these systems look like in the standard picture and in some modified picture, in some picture where physics is different, so that we can see how much we could learn from the observations that we're going to have. And as I say, my real hope is that we see some deviation in our future observables that give us a clue, and then we're able to interpret these, hopefully, through these kind of simulations.
And Toby, if we have enough oil and natural gas in the next 5 years?
I would build a very big particle collider to see the strings.
Yes.
But that probably not possible in the next 5 years, right?
No, but I'm being optimistic.
I don't know if this is within the realm of this conversation, but if I'm right, in cosmology, one of the fundamental ideas is that the early universe underwent a a very rapid acceleration called inflation, I think. Is there any theoretical explanation for that? And if not, why not?
So it does fall in the framework we've been talking about. The theory of inflation was written down, I guess, in the 80s. It was originally written down to account for why the universe looks so similar in different directions. This idea that it got very, very big very early on, and all we see is what was originally a tiny, tiny little patch of that got blown up. Now, what it then did later, and in fact Stephen Hawking was one of the people who worked on this, was the understanding that it not only accounts for this very homogeneous looking space and time that we live in, universe, but also it accounts for the very small deviations away from being exactly homogeneous, because quantum mechanics tells you you can never have anything exactly perfectly undisturbed, if you like. There's always little quantum fluctuations. And so one of the most beautiful ideas in cosmology is that actually all of the structures we see today, all of the complications and local bits of matter sitting around in our universe today, came from quantum fluctuations during inflation. So little quantum fluctuations during inflation got stretched, and through the process of inflation and what happened later, then grew under gravity, because gravity wants to make matter clump together more and more. So the quantum fluctuations set up a very small ripples on the surface of something that looked very homogeneous, but then those ripples grew into, in the end, galaxies, clusters of galaxies, and us that we see today. Now, that's an incredibly beautiful picture. The catch is that we only can see very indirectly the result of all of this. So what we really see is something called the cosmic microwave background. We see the distribution of structure today, and it's compatible with this idea of inflation. And in fact, nowadays we're getting to the point where we can even say, yes, this inflation model works and this one doesn't. So we can be a bit discriminating. But it's very difficult to know whether that's the only explanation or whether there's something else that gives the same phenomena. It's compelling that it could be that, and it certainly exists within these frameworks, but it's far from resolved. Some people will tell you, obviously it's true, but I think they're not being honest. That said, no one quite understands why it started. So the really big problem in cosmology that we've never, people really haven't made much progress on since Stephen Hawking's ideas in the 80s, like long ago, is why did it start so that, for example, inflation could then happen. In fact, Katy's done some very important work in these directions. But it's still an open question, why the universe began, which is, I think, to many people, like the really big philosophical question. Why is it the way it is? Where did it all come from?
I agree with Toby. I mean, yeah, so if you rewind the universe beyond inflation, so in a way, inflation kind of pushes the problem a bit further back, that you end up still with this idea that you must have a singularity at the beginning of the universe. And as I said, singularity means we don't know. So, again, we end up with this point where we don't know what's happening.
Looking into the future, you talked about improvements in telescope technology being a source of information, artificial intelligence also developing. How far is that going to help or hinder, given the people that come with it sometimes?
I'm not going to let you take that one, Toby. Toby will only be very pessimistic.
It's a no from me.
It's a no from Toby. So I'm, it's a new tool, and, a tool can be helpful or it can be not helpful. I actually think there's real potential for it to see connections between areas that haven't previously been connected before. So one of the things is when you work in physics, you realize that people are very specialized in what they do. And, you're very in your particular strand of physics and you understand it very well. And to, understand all the possible strands of physics is, I think, beyond most human capacity, right? So you can hope that these AI, which are really about pattern recognition, will recognize some pattern between these different threads that, a human couldn't get their head round. So it could help. But then we had this question earlier about, but does that really, if it gives you the answer 42, what do you do with that answer? So, yeah, maybe it will help us to, give us the answer, but we don't perhaps still understand the question.
In modern physics, especially quantum theory and cosmology, the role of the observer is still not fully understood. Do you think it's possible that consciousness could play a fundamental role in space-time itself, rather than being something that emerges from it?
No, go for it, Toby.
I think consciousness is a very interesting question, and I mean, there's two ways it can go. Either physics explains it, and we just have to deal with that, and that's it. There's nothing more than, wet stuff, or it's something else, not described by physics, current physics, in which case it's pretty weird. And we're in this interesting situation at the moment where basically physics can't explain it satisfactorily, but it's completely plausible it will. But we honestly just don't know. And it's a very, very interesting question. I think AI probably will shed quite a lot of light on this issue in years to come, actually, personally. Now, if there really is something beyond the laws of physics, I mean, well, you could then argue, well, actually, it is just part of the laws of physics and we don't understand the laws of physics fully. That would be huge. It would obviously be, whether it plays a role in space and time, I don't, I really wouldn't have any idea. But I think it's a deeply human question. It probably, I would imagine, has little impact on the universe, and cosmology and so on. This is really a question about our brains and our perception of the universe. But, who knows? Who knows? I mean, as we all famously know, I mean, we all can't be sure we all exist. So, once we, physics is more modest in some sense. It's trying to predict quite concrete answers to quite concrete questions that humans ask. There are then much bigger questions one can then ask, and physics doesn't really have very much to say about those currently, I would say. But they're very interesting.
I was quite surprised, Toby, when you said you were pessimistic. I'd always thought to work like at the edge of perception in the field that you are, you almost have to be quite brave and optimistic. So I was always curious about people who work in this field. You talked about the original string theory getting replaced quite quickly. Is that something that you, just on a human level, is that something that you worry about working in this field? Like, someone could come along and, like, even within my lifetime, 10, 15 years, and just replace and undo all the work that I'm doing? Or is that something you don't worry about because you sort of have to not to?
Do you know, I mean, it's what we want. I personally don't care whether I'm right. I would like us to understand better collectively, my colleagues and everyone, to understand what the answer is. That's why I'm in it. Not for me personally to be correct. So if someone could come along and say, actually, this is all wrong, that would be huge progress. Because then we would know something for sure that we don't know now. And of course, most theories that have been written down have been wrong. What we're working with today is the ones that weren't proven to be wrong yet. If the mathematicians can get their act together, and then they really look at string theory closely, and then we can we can really understand at a deep level, it may be shown to be inconsistent mathematically. Maybe the whole structure of string theory is just wrong, and that would be huge progress. That's exactly what we're looking for. So being wrong is almost as good as being right.
I guess I would also say, often the motivation for what we do is also not about having the answer. It's also about understanding things more deeply. So this a bit links to this question of AI, and I think it's why a lot of physicists are actually quite depressed by the idea of AI making contributions, is because we don't do this to know the answer. Okay, we do, but what we actually enjoy, like what I really enjoy, is actually doing the research and thinking of new ideas and trying to put them together, seeing that they don't fit. Okay, now let me try a different way. This whole process is what's really rich and creative and that we really enjoy in our jobs. So we're a little bit afraid of that being taken away from us, I think.
Thank you for that. And it's 5 years' time. Your grant has run out. You've got the T-shirt with the theory of everything expressed on there. What are you going to do next?
What are we all going to do next in 5 years' time? I think is the interesting question. I think if your question is if we genuinely found the theory of everything in the next 5 years, what would we do? Blue skies research, the whole point of it is to, in the end, enable us to do new things. So the end goal, I suppose, is not really to write down the theory of everything. Once we've got the theory of everything, we want to then understand what we can do with the theory of everything. You know, so I suppose we would then start looking at, well, how can I build a better mobile phone using my theory of quantum gravity? I'm joking in part, but I mean, of course, much of the technology we have today originated in the science of 100 years ago, and often very surprising. I mean, obviously, nuclear. I mean, it shouldn't be underestimated. I mean, Einstein talked about E equals mc squared and this idea that mass could convert into energy in 1905, and then already within 35 years, nuclear transitions were being harnessed as technology. That's incredibly quick. No one would have predicted that in 1905. I mean, no one. So, part of me worries actually that if we do write down theory of everything, it's, we're then talking about energy scales way beyond anything we can even comprehend now. And I don't know what will be possible in the future using it. But I guess people would start to think about that.
Wormholes, warp drives.
Wormholes, warp drives, yeah, exactly.
You said that if we had a large enough collider, then we could probably see string. And when you said that, I was curious because right now, obviously, we have classical photon telescopes or microscopes. We have electron microscopes. As far as I know, the string itself, it's like Planck length size-ish. Is it possible you would just never actually be able to see it, as it would be too many magnitudes of times smaller than anything else we could ever discover?
I think there's a question of what's possible today, what's possible in 1,000 years, what's possible in... it's very difficult to predict what's possible in the future. And people who do it usually get terribly unstuck because there's always surprises. Things you think you should be able to do, often you can't do. And things you never even thought of are actually what you'll end up doing. It is, there's two issues. One, yes, there's many orders of magnitude beyond where we are now. If you really wanted to see strings, if the world was made of strings, they are many, many orders of magnitude beyond where we are now. Does that mean you couldn't build a collider that big? Well, we certainly can't, but could some civilization, maybe powered by black holes or goodness knows what? I don't know. It's difficult to predict, but there are more fundamental issues. So, for example, if you really collide things at very high energies, actually what you do is you form little black holes. So does that process mean that it's difficult to see the strings? So once you start colliding things and getting exactly as you said, Planck scale energies, that's exactly when you start creating little black holes. So there may be a sort of cosmic conspiracy that says even if you could build a collider that big, black holes will sort of hide behind all this interesting stuff that you really wanted to see. The black holes will actually sort of swallow it up and stop you seeing it. Now, essentially we're just not quite sure, but in principle there isn't a physical obstruction, just a massive technological one to seeing them. But as Katy was saying earlier, maybe it's just easier. There'll be hints from cosmology, or we'll see something directly from cosmology.
On the question of the theory of everything, if you actually reach that, halcyon moment, wouldn't it be out of date before it even got to publication? Isn't it a moving target that can't ever be achieved? And isn't it what Katy said, the struggles of things?
Yeah, so I think if we did write down the theory of everything that unified quantum mechanics and gravity, we would very quickly find something else that was a problem. So, that might solve that, but then would it explain dark energy? Maybe it still doesn't, and then there's still something to figure out. Or even if you solve that, it doesn't necessarily tell you what happened at the beginning of the universe, right? So the beginning of the universe, even if you knew the theory of quantum gravity, you might not understand why it gave you a certain initial state for our universe. So my guess is that we would never stop. And maybe we wouldn't want to stop, as you kind of allude to, right? But my feeling is there will always be more problems to solve, I hope.
Just to say, I mean, there's literally the theory of everything, and then there's a theory of everything we could possibly observe. And it's not impossible that we could write down the theory of everything we could possibly observe, and then whether there's more beyond it is a sort of metaphysical question that we may never be able to answer. Is there some other universe out there that we can't possibly ever observe or see? It's just not a physical question we can even ask.
Am I right in thinking there have been experiments at the quantum level where you can't identify the cause and effect, or you can't see the path of causality?
I think there have been some claims that things travel faster than light. Maybe that's what you're referring to, but I think it's a bit more complicated, and so I think that no, there's nothing definitive of that nature. So people have been, there is this idea maybe because of the quantum uncertainty, you could travel a little bit faster than light. And so some experiments have looked at that. But I think a proper interpretation of the results is that actually, no, nothing travels faster than the speed of light. And in our theories of particle physics, which are really the setting that you should think about this, rather than some lab experiment, but really our theories of particle physics test this at places like CERN pretty exquisitely. They really build in Einstein's constraint that nothing travels faster than the speed of light pretty rigidly. So it would be a very big deal if that were true. And because everything works in particle physics, things really do work remarkably, completely in line with what the math says to an unbelievable degree. In the sense, there are things that you can measure, you can predict to sort of 12 digits precision, and then people can actually measure these days and measure 12 digits of precision, and they agree. And this is a prediction versus observation, that we can describe the universe that accurately is astonishing, but relies precisely on things like this underlying structure of special relativity, which forbids things traveling faster than the speed of light. So no, I don't believe there's anything conclusive or convincing that way.
So I guess I would just mention things like wormholes that occur in gravitational theories. Sorry, Toby.
Yeah.
So I mean, yes. So causality is kind of baked into all of our theories, and it's so fundamental that it's like the zeroth law of physics. But even just in classical gravity, you can get situations where if you have wormholes, you can somehow travel backwards in time, and you could then kill your grandparents or something like that. So you break causality. And, this is one of the reasons why we think that wormholes don't exist, because in a sense, if they did, you would potentially do things like this and create these kind of paradoxes. So yeah, it is at some level an assumption that maybe could be broken. Maybe causality is emergent, as we said, in some way. But I think that most physicists really kind of deeply believe that things should be causal.